Something is moving through the inner solar system right now that, according to everything we think we know, shouldn't exist. I don't mean it shouldn't be here. The galaxy is a vast, dynamic place, and the gravitational tides between stars inevitably fling debris across the interstellar void. We have seen these visitors before. No, what I mean is far more profound and unsettling. It shouldn't be possible for this object to behave the way it is behaving. Every principle of orbital mechanics, every equation governing plasma physics, every model we use to predict the motion of celestial bodies states unequivocally that this object, designated 3I Atlas, should have been deflected. It should have been pushed, even slightly, off its razor-precise predicted course when our sun, in a fit of cosmic fury, threw everything it had directly at it. But it wasn't. The data is clear, and for those who understand its implications, shocking. It didn't slow, it didn't swerve, it didn't even flinch. This isn't just a story about a rock from another star. This is a story that challenges the very foundations of our understanding of how objects interact with the violent environment of a star. On July 1st, 2025, the Atlas Survey Telescope in Chile recorded a faint, unremarkable smudge moving against the backdrop of fixed stars. Such discoveries are routine, but within hours, as orbital data poured in from observatories around the world, astronomers realized this was anything but routine. The trajectory wasn't a closed ellipse, the familiar path of a comet or asteroid bound to our sun. It was a hyperbola, an open escape curve, the mathematical signature of an object that does not belong here. This was the third confirmed interstellar visitor ever detected, and it was given a name that sounds more like a cipher than a celestial body, 3I Atlas. The calculations revealed an orbital eccentricity of around 6.1. For context, any value above 1.0 indicates an object is not gravitationally bound to the sun, but 6 is absurdly, wildly hyperbolic. This thing is a true interstellar vagabond, moving at a staggering 60 kilometers per second relative to the sun. It came from the depths of the galactic thick disk, a region of ancient stars, potentially billions of years older than our own solar system, and it is merely cutting through our neighborhood on a one-way trip to somewhere else in the Milky Way. Before moving forward, I want to ask you something. Let me know where in the world you're watching this from and what time it is there. The fact that we can share this mystery in real time across the globe is part of what makes it so incredible. And if you want to follow every twist and turn of this unfolding cosmic detective story, make sure to subscribe. You won't want to miss a single update. Let's go back to the story. The European Space Agency and a global network of telescopes began tracking it meticulously. They calculated its perihelion, its closest approach to the Sun, for late October 2025, at a distance of 135 astronomical units, just inside the orbit of Mars. It would be close enough to feel the Sun's intense heat, but not so close as to be vaporized. Then, the Hubble Space Telescope turned its gaze upon it on July 21st, revealing a classic cometary structure, a central nucleus, a glowing coma of gas and dust, and a tail being swept back by the solar wind. It looked normal, but the James Webb Space Telescope soon revealed the first clue that 3I Atlas was different. Its spectroscopy showed a coma dominated by carbon dioxide, not the water vapor and carbon monoxide mix typical of solar system comets. This was our first hint that the chemistry of this visitor was alien, shaped in a stellar nursery with conditions different from our own. The plot thickened in early October when 3I Atlas passed close to Mars, and orbiters like the ExoMars Trace gas orbiter confirmed its position was exactly where predictions said it would be. No surprises. Then, it did what all objects moving between the Sun and Earth eventually do. It passed behind the Sun, a period astronomers call superior conjunction. It vanished into the overwhelming glare invisible to conventional telescopes. This is where our story takes its first sharp turn into the truly strange, and where I need you to stay with me, because what happened next in the hidden space behind the Sun defies belief and may just force us to rewrite the textbooks. When 3I Atlas disappeared behind the Sun, the only way to see it was through the specialized eyes of coronagraphs, instruments, on satellites like GOES-19, and the Solar and Heliospheric Observatory, SOHO, that use an occulting disk to block the blinding light of the Sun's photosphere, revealing the faint, ethereal corona and the space immediately around our star. It was here, in the analysis of these coronagraph frames by a global network of dedicated amateur and professional astronomers, that the next chapter of the 3I Atlas mystery began to unfold. Independent observers, meticulously passing through publicly available data, started reporting an incredible discovery. They claimed they could see it, a faint, ghostly smudge moving through the chronograph imagery in late October, exactly where the predicted ephemeris said it should be. Frame by frame, day by day, this tiny speck of reflected light crept along its calculated path through one of the most hostile environments in the solar system, the immediate vicinity of our actively erupting star. It was a remarkable feat of detection, but what made it extraordinary was the context. For during this exact same period, while 3I Atlas was hidden from our direct view, solar observatories recorded something significant happening on the far side of the Sun. Not from the hemisphere facing Earth, which is why it didn't make mainstream news, but from active regions rotating away from our view. According to emerging reports from those analyzing solar weather logs and helioseismology data, the Sun unleashed 3 massive coronal mass ejections in rapid succession. These weren't mere puffs of solar wind. A CME is a physical eruption of the Sun's corona, a billion-ton blast of magnetized plasma torn from the Sun's atmosphere and hurled into space at speeds that can exceed 1,000 kilometers per second. And the critical, spine-chilling detail was this. The timing and the trajectory of these 3 CMEs aligned almost perfectly with the predicted position of 3I Atlas. Picture the scene from a cosmic perspective. On one side of the Sun, Earth goes about its business, largely unaware. On the opposite side, a tiny interstellar intruder, barely a few kilometers across, is making its closest approach to the stellar inferno. And from the surface of the Sun itself, 3 separate, gargantuan eruptions of solar fury launch. Their expanding clouds of ionized gas and twisted magnetic fields converging on the precise point in space where this visitor is located. It was as if the Sun itself had taken aim and fired a plasma cannon. Not once, not twice, but 3 times in quick succession, all directed at this one, small, silent wanderer from the void. The laws of physics are clear about what should have happened next. When 3I Atlas disappeared behind the Sun, the only way to see it was through the specialized eyes of coronagraphs, instruments on satellites like GOES-19 and the Solar and Heliospheric Observatory, SOHO, that use an occulting disk to block the blinding light of the Sun's photosphere, revealing the faint ethereal corona and the space immediately around our star. It was here, in the analysis of these coronagraph frames by a global network of dedicated amateur and professional astronomers, that the next chapter of the 3I Atlas mystery began to unfold. Independent observers, meticulously passing through publicly available data, started reporting an incredible discovery. They claimed they could see it, a faint, ghostly smudge moving through the chronograph imagery in late October, exactly where the predicted ephemeris said it should be. Frame by frame, day by day, this tiny speck of reflected light crept along, its calculated path through one of the most hostile environments in the solar system, the immediate vicinity of our actively erupting star. It was a remarkable feat of detection, but what made it extraordinary was the context. For during this exact same period, while 3I Atlas was hidden from our direct view, solar observatories recorded something significant happening on the far side of the Sun. Not from the hemisphere facing Earth, which is why it didn't make mainstream news, but from active regions rotating away from our view. According to emerging reports from those analyzing solar weather logs and helioseismology data, the Sun unleashed 3 massive coronal mass ejections in rapid succession. These weren't mere puffs of solar wind. A CME is a physical eruption of the Sun's corona, a billion-ton blast of magnetized plasma torn from the Sun's atmosphere and hurled into space at speeds that can exceed 1,000 kilometers per second. And the critical, spine-chilling detail was this. The timing and the trajectory of these 3 CMEs aligned almost perfectly with the predicted position of 3I Atlas. Picture the scene from a cosmic perspective. On one side of the Sun, Earth goes about its business, largely unaware. On the opposite side, a tiny interstellar intruder, barely a few kilometers across, is making its closest approach to the stellar inferno. And from the surface of the Sun itself, 3 separate gargantuan eruptions of solar fury launch. There, expanding clouds of ionized gas and twisted magnetic fields, converging on the precise point in space where this visitor is located. It was as if the sun itself had taken aim and fired a plasma cannon, not once, not twice, but 3 times in quick succession, all directed at this one, small, silent wanderer from the void. The laws of physics are clear about what should have happened next. To understand why the non-response of 3I Atlas is so deeply troubling, we must first grasp the sheer, violent power of a coronal mass ejection. A CME is not a solar flare, which is a burst of light and radiation. A CME is a physical thing, a colossal cloud of magnetized plasma, a chunk of the sun's own atmosphere being violently ejected into space. When one of these events launches, it carries billions of tons of ionized hydrogen, helium, and heavier elements, all threaded with chaotic, tangled magnetic field lines. This magnetized plasma carries immense momentum. When a CME hits Earth's magnetosphere, that momentum transfer causes geomagnetic storms, potentially disrupting power grids and creating brilliant auroras. Now imagine what should happen when such a force encounters a small comet. The comet has no global magnetic shield. It is a solid nucleus surrounded by a tenuous coma of gas and dust. When the leading edge of a CME slams into it, the first effect is a shockwave that compresses the coma and can brighten or even strip away the tail. But more fundamentally, there should be a transfer of momentum. Some of the vast momentum of the CME should be imparted to the comet's nucleus, giving it a push. Let's put some rough numbers to this. Assume a conservative CME mass of 10 trillion kilograms traveling at 1,000 km/s. The momentum is staggering. If 3I Atlas has a nucleus about 2.8 kilometers in diameter, as Hubble data suggests, and a density similar to a typical comet like 67P, its mass would be around 6 trillion kilograms. If even 1% of the CME's momentum transferred to the nucleus in a head-on collision, the comet would experience a velocity change on the order of 20 meters per second. That might not sound like much, but over the days and weeks following such an impact, that small change compounds. The comet's position would shift noticeably from its predicted path. It would arrive at subsequent orbital points slightly early or late. Our astrometric measurements, especially with modern technology, should be able to detect this deviation with ease. Now, multiply that by 3 separate CME impacts. We are not talking about a subtle effect buried in the noise. We should be looking at an orbital path that is clearly measurably different from the prediction. But the coronagraph observations that emerged after the conjunction tell a different story, a story that defies this basic physics. The object that re-emerged from behind the sun, the faint smudge that continued its journey outward, was exactly, perfectly, undeviatingly, where the original ephemeris, calculated months before any CMEs erupted, predicted it would be. No deflection, no change in velocity, no deviation in its orbital plane. It was as if those 3 gargantuan eruptions of solar plasma, carrying enough energy to alter the orbits of small worlds, had simply passed through it or around it without imparting any net force whatsoever. The data suggested that 3I Atlas had weathered a solar storm of biblical proportions and hadn't budged an inch. Faced with an observational conundrum of this magnitude, the scientific mind must explore all possibilities, even those that sound like they belong in the realm of science fiction. This brings us to the most speculative yet fascinating hypothesis emerging from certain circles in the astronomy and plasma physics communities. The idea that 3I Atlas is not a passive piece of cosmic driftwood, but an object that is actively and electromagnetically interacting with the sun. This short-circuit hypothesis proposes a feedback loop of breathtaking audacity. It suggests that 3I Atlas, through its unusual plasma environment, is somehow perturbing the sun's own magnetic field. The sun's corona is a seething ocean of magnetically dominated plasma where field lines store enormous energy. When these stressed field lines reconfigure in a process called magnetic reconnection, they release that energy in the form of solar flares and CMEs. The hypothesis is that the presence of 3I Atlas, with its CO2-rich and potentially highly conductive coma, acts as a trigger. Its movement through the corona could destabilize already stressed magnetic structures, facilitating reconnection and launching a CME. Crucially, the CME would be launched from the region of disturbance, which is, by definition, the region where the object is located. In this scenario, 3I Atlas is triggering the very gun pointed at itself. But the hypothesis doesn't stop there. It further proposes that the object's plasma environment also provides a shield. The induced currents and magnetic fields within its large, diffuse coma could interact with the magnetic structure of the incoming CME through complex electromagnetic interactions, the physics of which are governed by magnetohydrodynamics. The forces of the impact could be redistributed. The Lorentz force, which describes how charged particles move in a magnetic field, could generate forces that cancel out the net momentum transfer to the solid nucleus. The coma could act as a kind of magnetic sail or cushion, absorbing and redirecting the CME's energy into heating and compressing the plasma around it, rather than pushing the core itself. This is not magic. It is frontier plasma physics. Harkening back to the work of Nobel laureate Hannes Alfvén, who emphasized the primacy of electromagnetic forces in cosmic plasmas. While mainstream solar physics would be deeply skeptical, arguing that the scales and energy budgets don't match, the hypothesis remains just barely plausible to be worth serious consideration. If there is even a kernel of truth to this, we are not just looking at a weird comet. We are looking at a new class of astrophysical phenomenon, where small interstellar bodies can engage in a complex electromagnetic dialogue with the stars they visit. To properly gauge the depth of this mystery, we must move from qualitative wonder to quantitative rigor. Let's establish exactly what we know about 3I Atlas and calculate the expected deflection with as much precision as the data allows. Starting with the object itself, Hubble's observations constrain the nucleus to a diameter of no more than 2.8 kilometers, assuming a spherical shape and a density consistent with a porous, icy comet like 67P Churyumov-Gerasimenko, around 0.5 grams per cubic centimeter. We arrive at a mass of roughly 5.5 trillion kilograms. This is our baseline. Now let's model a CME impact. A typical large CME can contain on the order of 10 mom or 16 grams of material, 10 trillion kilograms, moving at 1,000 kilometers s. The momentum of such an event is colossal. If we assume the effective cross-sectional area for momentum transfer is the geometric area of the nucleus, about 6 square kilometers, and the CME lasts for an hour, a non-trivial fraction of its mass could interact with the comet. The math, even with conservative assumptions, suggests a velocity change, delta V, of several meters per second per significant impact. With 3 impacts, the cumulative effect should be unmistakable. So why didn't it happen? We are left with a limited set of possibilities, each with its own implications. Possibility 1, the CMEs missed. Space is vast, and CMEs are not solid bullets but expanding clouds. Perhaps the dense cores of the plasma clouds passed by 3I Atlas without a direct hit, and the tenuous outer layers simply washed over the coma without transferring significant momentum. This is the simplest and most conservative explanation, but it requires a fortunate coincidence of 3 near misses. Possibility 2, our mass estimate is wrong. If 3I Atlas is far more massive than it appears, if its density is that of solid rock or metal, say 35G CM3, then the same momentum transfer would result in a much smaller velocity change, potentially below the detection threshold of the coronagraph astrometry. But this raises another question. If it's a dense rocky body, why is it outgassing so vigorously like a comet? Possibility 3, the exotic one. The momentum was somehow negated or redirected through electromagnetic means, as outlined in the short-circuit hypothesis. The mere fact that we are forced to consider such a possibility highlights how deeply anomalous the trajectory of 3I Atlas appears to be. It forces us to confront the limits of our models and asks us whether we are seeing a statistical fluke or the first glimpse of a new physical principle at work. 2. Understand whether 3I Atlas is uniquely strange or part of a pattern. We must look at its interstellar predecessors. The first, Oumuamua, discovered in 2017, was bizarre in its own right. It had an extreme, elongated shape and showed a small but definite non-gravitational acceleration as it departed the solar system, yet it displayed no visible coma or tail. This acceleration without outgassing fueled intense debate, with explanations ranging from the sublimation of exotic ices like nitrogen to, in more speculative proposals, it being a light sail from an alien civilization. In stark contrast, the second visitor, 2I Borisov, discovered in 2019, was almost comfortingly normal. It looked and behaved like a textbook comet with a clear coma and tail, and its spectroscopy revealed familiar molecules like water and carbon monoxide. It was a reminder that some interstellar objects can be quite similar to those in our own solar system. Now, 3I Atlas presents a third, distinct profile. It is larger than both, actively outgassing like Borisov, but with a strange CO2-dominated chemistry. Most importantly, it is the first to potentially exhibit a mysterious resistance to external forces from the Sun itself. This trio of visitors tells us a powerful story. The population of interstellar objects is not monolithic. It is diverse, possibly reflecting the immense variety of formation environments and histories across the galaxy. Oumuamua might have been a fragment of a Pluto-like world from another system. Borisov, a classic comet ejected from its Oort cloud, and 3I Atlas, what? Perhaps something even more exotic. Its behavior suggests it might be an object that has been processed by billions of years of travel, its structure and properties altered by cosmic rays and stellar encounters in ways we are only beginning to imagine. The weird might be the normal for this galactic population, and our own solar system's comets and asteroids may be the parochial exceptions. A crucial part of this story is acknowledging what we don't know. The claims about the CME impacts and the lack of deflection are, as of now, based largely on analysis of public data by independent researchers. They have not yet been formally published in a peer-reviewed journal. This does not make them false. Some of the most important astronomical discoveries have come from amateurs, but it does demand a higher degree of caution and skepticism. So, what data might exist that we haven't seen? High-cadence coronagraph imagery from satellites like SOHO exists, but processing it to extract the precise astrometry of a faint comet is specialized work that may not have been completed by official mission teams. In situ plasma measurements from spacecraft like the Parker Solar Probe or Solar Orbiter could be invaluable. If any spacecraft were fortuitously positioned downstream of 3I Atlas, their instruments could have recorded the plasma and magnetic field disturbances from both the object and the CMEs, providing a definitive record of the interaction. But this data often has an embargo period for the mission teams to conduct their analysis. Furthermore, detailed helioseismology data could confirm the existence and strength of the far-side active regions that supposedly produce the CMEs. The scientific process is methodical and often slow. Data is collected, calibrated, analyzed, submitted for peer review, and then published. This process is designed to weed out errors and over-interpretations. The full vetted story of 3I Atlas's perihelion passage may still be months away from being officially revealed. This hidden data problem is both a challenge and an opportunity. It challenges us to resist jumping to conclusions, but it also presents the thrilling possibility that there is more to this story, waiting in the archives of satellites and observatories, that will eventually come to light and either solve the mystery or deepen it further. We have been calling 3I Atlas a comet because it has a coma and a tail. But what if that classification is a profound error? What if it is something else entirely? An object type that doesn't exist in our solar system, or is so rare we've never encountered it? Let's explore the possibilities. First, it could be a fragment of a shattered exoplanet. Imagine a rocky or metallic world torn apart by a cosmic collision or a passing star. A fragment of its core, rich in minerals and possibly containing carbonates, could explain the high density needed to resist the CMEs and the CO2 outgassing from the breakdown of carbonates upon heating. Second, it could be an ancient relic from the early galaxy, a population the 2 object formed from material with much lower metallicity than our Sun. Its chemical composition and internal structure could be fundamentally different from anything that formed in our more metal-rich corner of the galaxy. Third, it could be a rubble pile with a complex layered structure, a porous, fluffy exterior surrounding a denser core. Such a structure could absorb the impact of a CME by compressing or shedding its outer layers, protecting the core from a net push. And fourth, there is the most remote possibility, the one that captures the public imagination, that it is an artificial construct, a probe. While there is zero evidence for this, and it remains the least likely scenario by an immense margin, we cannot a priori dismiss the possibility that a technologically advanced civilization could create a probe designed to withstand interstellar travel and close stellar encounters. perhaps using electromagnetic fields for propulsion or shielding. The way to distinguish between these possibilities is through further observation. High-resolution spectroscopy can search for unusual isotopic ratios. Detailed photometry can study its rotation and look for signs of an unusual shape or tumbling. Polarimetry can probe the properties of the dust in its coma. Each hypothesis makes different, testable predictions. The journey to understand 3I Atlas is, therefore, a journey in cosmic taxonomy, an attempt to fit a new and alien specimen into our catalogue of the universe, or to create a whole new category for it. As the story of 3I Atlas has captured public attention, a more speculative and controversial narrative has emerged, linking the object to solar activity and even terrestrial events. The claim is that the same active regions that allegedly launched CMEs at 3I Atlas in late October would, due to the Sun's 27-day rotation, swing into an Earth-facing position in mid-November. This, combined with a full or supermoon, is suggested by some to create a perfect storm that could trigger enhanced geomagnetic activity or even seismic events on Earth. It is vital to dissect this claim with scientific rigor. The first part is straightforward solar physics. Active regions do rotate with the Sun. If there were powerful regions on the far side, they would indeed become Earth-facing about 2 weeks later. This is normal. The second part is also well established. When these regions erupt and launch Earth-directed CMEs, they can cause geomagnetic storms. The third part, however, is where the science becomes tenuous. The connection between geomagnetic storms and earthquakes is not supported by mainstream geophysics. While tiny tidal stresses from the Moon can, in theory, act as a final trigger for a fault already on the verge of slipping, the forces from space weather are orders of magnitude too weak to significantly stress the Earth's crust. The narrative connecting an interstellar object to earthquakes via the Sun is a chain of correlations stacked on weak correlations. It is a compelling story that connects cosmic events to our daily lives, but it confuses correlation with causation. Large earthquakes happen regularly, so do full moons and periods of solar activity. By chance alone, they will occasionally coincide. The value in examining this narrative is not in its likely truth, but in the lesson it provides about critical thinking and the importance of demanding robust evidence for extraordinary claims, especially those that weave together disparate phenomena into a single, dramatic storyline. The clock is ticking on our opportunity to study 3I Atlas. Having passed perihelion in late October 2025, it is now on an outbound trajectory, moving away from the Sun at high speed. With every passing day, it grows fainter as the solar heating that drives its outgassing diminishes. Within weeks or months, it will likely fade beyond the practical reach of all but the largest telescopes, becoming just another anonymous dot of light lost among the stars, its secrets forever receding into the interstellar dark. This transience is the nature of interstellar visitors. We get one brief, precious chance to observe them. So what must be done now? The priorities are clear. First, continued precise astrometry. As the object moves farther out, any small deflection from the CME impacts would compound over time, making it easier to detect. If it remains perfectly on its original course, the mystery deepens. Second, continued spectroscopy to monitor how its coma composition changes as different volatiles freeze out at different temperatures, which could reveal layering in the nucleus. Third, high-resolution imaging to better constrain its size, shape, and rotation. We must also look to the Sun. If the active regions from late October are real and still active, they should now be visible on the Earth-facing side. Do they show unusual complexity or energy? Do they produce more eruptions? Furthermore, we must scour the data from other spacecraft. Did the Parker Solar Probe, the Solar Orbiter, or any Mars orbiter happen to pass through the plasma tail of 3I Atlas, or sample the aftermath of the CMEs? Such serendipitous in situ data would be invaluable. The story of 3I Atlas is a race against time, a collective effort by the global astronomical community to extract every possible photon of information from this enigmatic visitor before the window of opportunity slams shut. While we have been tracking 3I Atlas, the James Webb Space Telescope has been quietly revolutionizing a parallel field: exoplanet atmospheric science. In early 2025, JWST characterized the atmosphere of a distant exoplanet and found it to be dominated by carbon dioxide, with very little water vapor, a composition that challenges our standard planet formation models, which are based on our own solar system. This discovery provides a crucial context for 3I Atlas. Here we have an interstellar object with a coma also dominated by CO2, distinct from our native comets. This parallel is profound. It suggests that carbon dioxide-rich chemistry might be a common feature in other planetary systems, perhaps those that formed from molecular clouds with different carbon to oxygen ratios or under different thermal conditions. 3I Atlas, then, is not just a solitary oddity. It is a flying sample of a different kind of planetary chemistry. It is a piece of a distant exoplanetary system that we can study directly, however briefly. Its composition is a chemical fingerprint, telling a story about the conditions in the stellar nursery, where it was born billions of years ago. Every interstellar object we detect is a random sample from the galactic library, each carrying a unique chemical signature from its point of origin. The CO2 dominance of 3I Atlas and the exoplanet discovered by JWST together paint a picture of a galaxy far more chemically diverse than we had previously assumed from our limited sample of one solar system. The Sun itself has been a central character in this drama, and its behavior provides another layer of context. Solar Cycle 25, which we are currently in, has proven to be more active than initially forecast. In mid-2025, an unexpectedly powerful X-class solar flare and a fast-moving CME erupted from a region that did not appear particularly threatening, triggering a significant geomagnetic storm on Earth. This event was a stark reminder of the Sun's inherent unpredictability. Our models can predict general trends of the solar cycle, but forecasting the timing and power of specific eruptions from specific active regions remains a formidable challenge. This inherent volatility of the Sun is crucial to the 3I Atlas story. If the Sun can produce a major eruption from a seemingly benign region, then the claim that far-side active regions produced multiple CMEs is entirely plausible. The question is not if the Sun could do it, but whether it did it in a way that intersected 3I Atlas's path. The Sun's dynamic nature also complicates the search for causation. If we are looking for a signal of 3I Atlas influencing solar activity, we are searching for that signal within a system that is already noisy and unpredictable. Disentangling a potential external trigger from the Sun's own internal chaos is a monumental task, one that requires vast amounts of data and sophisticated statistical analysis. The violent awakening of the Sun in this cycle is a backdrop against which the 3I Atlas mystery is playing out, a reminder that we are observing a dynamic, living star whose moods we are only beginning to understand. The scale of modern astronomical data is so vast that human analysis alone is often insufficient. This is where artificial intelligence and machine learning are becoming indispensable tools, and they are highly relevant to the 3I Atlas enigma. Consider the challenge of finding a faint comet in coronagraph images, which are filled with the bright, structured corona, instrumental artifacts, and cosmic ray hits. Machine learning algorithms, trained on thousands of such images, can be taught to recognize the subtle signature of a comet, automating a process that is incredibly labor-intensive for humans. Similarly, ML models are now being used to forecast the arrival and strength of CMEs based on their initial appearance, often outperforming traditional physics-based models. Imagine applying such a tool to the 3I Atlas event. One could simulate the propagation of the alleged CMEs, model their interaction with a comet of various assumed masses and plasma properties, and determine the range of expected deflections. This would allow us to move from back-of-the-envelope calculations to a comprehensive exploration of the parameter space, identifying which scenarios are consistent with the observed lack of deflection. Machine learning is also transforming spectroscopy, automatically identifying molecular lines and measuring abundances from complex spectra, potentially picking up on subtle anomalies in 3I Atlas's chemical signature that a human might miss. These algorithms are powerful allies, but they are not oracles. They are limited by their training data. If interstellar objects have fundamentally new properties, an AI trained only on solar system comets might not recognize the anomaly. The combination of human curiosity and machine processing power is our best bet for solving the complex puzzles presented by visitors like 3I Atlas, allowing us to see patterns and connections in the data that would otherwise remain hidden. The mysteries of small bodies are not confined to the interstellar realm. Recent findings from asteroid sample return, missions like OSIRIS-REx, which returned material from asteroid Bennu and Hayabusa 2 from asteroid Ryugu, have revealed that even solar system asteroids are far more complex than we thought. They are not homogeneous rubble piles, but geologically rich bodies with evidence of aqueous alteration, heterogeneous compositions, and inclusions of unexpected, highly reflective materials. These missions teach us a humbling lesson. If objects from our own solar system, which formed from the same protoplanetary disk as Earth, can surprise us with their internal complexity, then we should absolutely expect interstellar objects, which formed in entirely different systems under unknown conditions, to be full of surprises. Their internal structure, density, and composition could be wildly different from our initial assumptions based on solar system analogues. This directly impacts the 3I Atlas mystery. Our mass estimate, and therefore our calculation of how much it should have been deflected, is based on these possibly flawed analogies. Furthermore, the study of pre-solar grains, tiny dust particles, found in meteorites that formed around other stars long before our sun was born, shows that material from different stellar environments carries distinct isotopic fingerprints. If we could hold a piece of 3I Atlas in a lab, we could likely determine what type of star it formed near. While we cannot do that, high-resolution spectroscopy might one day allow us to measure its isotopic ratios remotely. 3I Atlas is a messenger, and the messages it carries, in its light, its spectrum, its motion, are clues to the diversity and history of our galaxy, written in a language we are still learning to read. The story of 3I Atlas is not an isolated event. It is part of a broader pattern in modern astronomy, a field that is currently defined by the discovery of anomalies that challenge our existing categories and models. From the unexpected acceleration of Oumuamua to the inexplicable properties of some fast radio bursts, from exoplanet atmospheres that defy classification to gravitational wave sources that don't quite fit. We are living in an era where our new observational capabilities are consistently revealing a universe that is stranger, more diverse, and more wonderful than we had previously imagined. This is the classic pattern of scientific discovery. Every time we open a new window on the cosmos, be it radio, X-ray, infrared, or gravitational waves, we find phenomena we did not predict. Most of these anomalies, upon closer investigation, are eventually explained within the existing framework of physics, though often requiring us to expand our understanding of what is possible. A tiny fraction may point toward genuinely new physics. At this moment, 3I Atlas sits squarely in this frontier zone. It is an anomaly. The vast weight of probability suggests that its mysterious resilience will have a conventional explanation, perhaps a combination of fortunate CME misses and a slightly denser than expected nucleus. But we cannot know that until we have done the work. The process of investigation itself is what pushes science forward. By taking anomalies seriously, by subjecting them to rigorous scrutiny, we improve our models, refine our techniques, and prepare ourselves for the day when we encounter an anomaly that truly is revolutionary. 3I Atlas, regardless of the final outcome, has already served a vital purpose. It has made us question, calculate, and wonder. It has reminded us that the cosmos is not a static museum, but a dynamic, evolving, and often unpredictable system, and that we are just beginning to explore its deepest secrets. The detection of 3I Atlas marks not an endpoint, but a beginning, a preview of a coming revolution in our understanding of our galactic neighborhood. Our ability to find these visitors has been, until now, largely a matter of luck. They are faint, fast-moving, and their discovery has been a testament to the sharp eyes of both automated surveys and dedicated amateurs. But this era of serendipity is rapidly drawing to a close, soon to be replaced by an age of systematic discovery. The Vera C. Rubin Observatory, formerly known as the LSST, is poised to come online in the near future, and its impact will be nothing short of transformative. With its immense mirror and massive 3-gigapixel camera, it will scan the entire visible sky every few nights with unprecedented depth. This relentless, all-seeing eye will not only find interstellar objects with a frequency we can only dream of today, potentially several per year, but it will find them early, often while they are still far beyond the orbit of Jupiter. This early warning is critical. It provides the one thing we have always lacked with these visitors: time. Time to marshal the world's telescopes for coordinated observation campaigns across the electromagnetic spectrum. Time to study their pristine surfaces before solar heating begins to alter them. And, most tantalizingly, time to contemplate the once unthinkable, mounting a dedicated space mission to rendezvous with an interstellar object. The data we will gather from this future population will allow us to move from studying individual curiosities to understanding population statistics. We will be able to answer fundamental questions. What is the typical size distribution of interstellar objects? What is the distribution of their orbital velocities, telling us about their galactic origins? Are carbon dioxide-rich objects like 3I Atlas common, or a rare oddity? This statistical lens will allow us to peer back into the processes of planet formation and ejection across the galaxy, building a census of the building blocks that wander the void between stars. The story of 3I Atlas is therefore a crucial test case, a trial run for the protocols, the models, and the collaborative frameworks we will need to fully exploit the coming flood of discoveries from this new frontier of astronomy. The ultimate goal, the pinnacle of interstellar object science, is a mission that does not merely observe from a distance, but meets one of these visitors in deep space. The concept of a rapid response interstellar interceptor has been studied by space agencies for years, but the technical challenges are monumental. The primary obstacle is velocity. 3I Atlas is moving at 60 km/s relative to the Sun. To match speeds with such an object for a meaningful rendezvous, a spacecraft would need to achieve a similar hyperbolic excess velocity, a feat far beyond the capability of conventional chemical rockets, even with powerful gravitational assists. This demands revolutionary propulsion technologies. Solar electric propulsion, while efficient, provides too low a thrust for such a fast-paced mission. Nuclear thermal or nuclear electric propulsion could offer a viable path, providing a much higher specific impulse. The most promising, albeit distant, technology is some form of advanced propulsion like a solar sail, which, if deployed close to the Sun, could theoretically achieve the required velocities by riding on the momentum of photons themselves. The payoff, however, would be immeasurable. A spacecraft flying alongside 3I Atlas, or even impacting it to create an artificial crater for analysis, would provide data that would settle every debate we are currently having. A gamma ray or neutron spectrometer could measure its elemental composition directly. A magnetometer could definitively determine if it possesses an intrinsic magnetic field. A camera could map its surface in stunning detail, revealing its geology and history of impacts. A mass spectrometer could analyze the gases from its coma, and even the dust particles ejected from its surface, giving us a direct chemical and isotopic fingerprint of its origin system. Such a mission would transform 3I Atlas from a point of light and a set of spectral lines into a tangible world, a geologic entity with a story to tell. While a mission to 3I Atlas itself is now impossible, it is already receding too quickly. Its passage has provided the impetus to seriously develop the technologies and mission architectures needed so that when the next promising, early detected interstellar visitor is discovered, we will be ready to go. The strange behavior of 3I Atlas, particularly the short-circuit hypothesis, forces us to re-examine a branch of physics that often takes a back seat in astronomy: plasma cosmology and the profound role of electromagnetic forces on cosmic scales. For decades, the dominant paradigm in modeling cosmic phenomena has been gravity. We calculate the orbits of planets, the collapse of nebulae, and the dynamics of galaxies primarily through the lens of Newton and Einstein. Yet, the universe is 99% visible matter in the plasma state, an ionized gas suffused with magnetic fields and electric currents. The work of Hannes Alfvén, the Nobel laureate who pioneered magnetohydrodynamics, was a lifelong plea to take these electromagnetic forces seriously. He envisioned a plasma universe where vast filamentary currents flow through space, where magnetic fields can shape nebulae and accelerate particles to relativistic energies, and where interactions are often non-local and collective, rather than simple ballistic collisions. The standard model of cometary interactions with the solar wind is a relatively simple one. The solar wind impacts the coma, forming a bow shock and a tail. But what if, for an object with the right composition and conductivity, the interaction is far more complex? What if the moving comet, as a charged body traversing the Sun's magnetic field, acts as a unipolar inductor, generating powerful voltages that drive currents through its coma? These currents would, in turn, generate their own magnetic fields, creating a complex dynamic magnetic structure around the nucleus that could interact with the solar wind and CMEs in non-intuitive ways. This is not electric universe fringe theory, it is applied high-energy plasma physics. While the energy scales of the Sun dwarf those of a small comet, the hypothesis is not that 3I Atlas provides the energy for the CME, but that it acts as a catalyst. a trigger that releases energy already stored in the sun's stressed coronal magnetic fields. Its conducting coma could provide a short-circuit pathway that facilitates magnetic reconnection. Testing this would require in situ measurements we do not have, but it opens a new line of theoretical inquiry. Perhaps 3I Atlas is our first hint that in the complex plasma environment near a star, small bodies can play a more active role than mere passive driftwood, and that the circuits of the heliosphere are more easily disturbed than we thought. Beyond the immediate scientific questions of composition and physics, the existence and behavior of 3I Atlas carry deeper philosophical weight, forcing a reconsideration of our place in the cosmos. For centuries, we viewed our solar system as a largely isolated system. The comets of our Oort cloud were the outermost sentinels, bound by the sun's gravity, with the true interstellar void beyond being just that, a void. The discovery of interstellar objects shatters that illusion. The galaxy is not empty. It is teeming with material, a cosmic ocean through which our solar system sails, constantly encountering flotsam and jetsam from other stellar systems. 3I Atlas is a tangible piece of evidence that the processes of planet formation and destruction are not unique to us. They are universal. The material that came together to form Earth, the water that fills our oceans, the carbon that is the basis of our life. These are not special ingredients. They are common galactic resources, being mixed and distributed on a grand scale. The CO2 pouring from 3I Atlas is a message that the same elements, the same chemistry exists light years away. Furthermore, if objects like 3I Atlas are as common as early statistics suggest, then the exchange of material between star systems is a continuous, ongoing process. This has profound implications for the theory of panspermia, the idea that life itself could be spread from star to star aboard such rocky vessels. While 3I Atlas shows no sign of life, its very existence proves that the mechanism for such transfer is operational. A fragment from an Earth-like planet ejected by a giant impact could, in theory, carry microbial life across the immense distances between stars, protected within its rocky interior. 3I Atlas forces a cosmic perspective. We are not isolated. We are part of a vast interconnected galactic ecosystem, a participant in a continuous cycle of cosmic material that has been ongoing for billions of years. At its heart, the saga of 3I Atlas is a case study in the scientific method confronting an anomaly. How do we, as a species, deal with observations that do not neatly fit into our established boxes? The history of science is littered with anomalies that were later explained, from the precession of Mercury's orbit, eventually explained by general relativity, to the cosmic microwave background radiation, a key prediction of the Big Bang theory. The initial response is often a mix of skepticism, excitement, and a scramble to find a conventional explanation. We are witnessing this process in real time with 3I Atlas. The conservative approach, embodied by Occam's razor, is to exhaust all mundane explanations before venturing into the exotic. The CMEs missed. The mass is higher. The astrometry is less precise than claimed. This is a healthy and necessary process. It prevents science from chasing every phantom. Yet, there is also a danger in being too conservative, in dismissing an anomaly too quickly, because it is inconvenient or challenges deeply held beliefs. The key is to maintain a delicate balance, a steadfast commitment to rigorous evidence and parsimony, coupled with a creative openness to the possibility that nature may be more inventive than our current models. The short-circuit hypothesis, while speculative, is valuable not necessarily because it is correct, but because it forces us to ask new questions and consider our data from a different angle. It pushes the boundaries of the plausible. Even if it is ultimately rejected, the process of testing it will likely lead to new insights into plasma-comet interactions that we would not have gained otherwise. The true value of an anomaly like 3I Atlas is that it acts as a stress test for our scientific frameworks. It reveals the weak points in our models, the gaps in our data, and the limits of our imagination. By grappling with it seriously, we do not just learn about one strange object. We learn about the strengths and weaknesses of our own process of inquiry, and we emerge with a more robust and nuanced understanding of the universe, regardless of the outcome. The story of 3I Atlas has captured a global audience in a way that most deep space astronomical discoveries do not. There is a compelling, almost narrative quality to it. A mysterious stranger from a distant realm, a hostile confrontation with a star, and an inexplicable survival. This public engagement is not a trivial side effect. It is a vital part of the modern scientific ecosystem. The initial detections of the object in coronagraph data did not come from a major space agency press release, but from the diligent work of amateur astronomers and citizen scientists sifting through publicly available data. This is the democratization of discovery, enabled by the internet and open data policies. Platforms like YouTube, Reddit, and X have become the modern-day town squares where these discoveries are debated, dissected, and sometimes sensationalized. This has immense power for good. It inspires a new generation of scientists, fosters science literacy, and creates a constituency that supports funding for basic research. However, it also comes with challenges. The line between informed speculation and unfounded conspiracy can blur. The compelling narrative of 3I Atlas short-circuiting the sun can easily be stripped of its necessary scientific caveats and presented as established fact. This places a new responsibility on scientists and science communicators to be transparent about uncertainties while still conveying the excitement of the unknown. The public's fascination with 3I Atlas is a resource. It is an opportunity to teach not just facts about comets, but the very process of science, the slow, messy, collaborative, and self-correcting endeavor of building reliable knowledge about the world. The story is a gateway to discussing orbital mechanics, plasma physics, and the scientific method itself. In this sense, 3I Atlas is more than a scientific target. It is a cultural touchstone and a powerful tool for public education. To fully appreciate the alien nature of 3I Atlas, we must perform a detailed comparative anatomy, placing it side by side with the comets we know best, those from our own solar system. Our home system comets fall into rough categories. Jupiter family comets, like 67P, are relatively small, have short orbital periods, and have been thermally processed by repeated close passes to the Sun. They are often water-rich. Long-period comets from the Oort cloud, like Hale-Bopp, are larger, more pristine, and can also be water-dominated, though with varying amounts of CO and CO2. Then there are the Manx comets, rocky objects that have comet-like orbits but show little to no activity, perhaps representing the depleted cores of ancient comets. 3I Atlas fits none of these categories neatly. Its hyperbola immediately sets it apart. Its size is larger than most Jupiter family comets, but smaller than a giant like Hale-Bopp. Its activity level is significant, yet its dominant gas, CO2, is unusual. In our solar system, CO2 is common but is typically a secondary volatile to water. For it to be the primary gas suggests a formation environment that was either too warm for water ice to condense in abundance, or a subsequent history that stripped away the more volatile water. Furthermore, the apparent lack of a measurable non-gravitational force from its outgassing is puzzling. Active comets experience a small rocket effect from the asymmetric jetting of gas, which subtly alters their orbits. The pre-perihelion orbit of 3I Atlas showed little evidence of this, suggesting its outgassing was perhaps more symmetric, or that its mass was too great for the force to have a noticeable effect. This comparative analysis underscores that 3I Atlas is not merely a solar system comet that happened to be ejected. It is a product of a different environment, with a different formation history and a different chemical inventory. It is a genuine exocomet, and its differences are the very features that make it scientifically precious. Contemplating the journey of 3I Atlas is an exercise in cosmic humility. Based on its high velocity and trajectory, it likely originated from the galactic thick disk, a halo of ancient stars that surrounds the Milky Way's central bulge. This population of stars is billions of years older than our Sun. This means that 3I Atlas could be older than our entire solar system. It has been wandering the interstellar darkness since a time before the Earth formed. Its journey has been one of profound isolation and endurance. It has been bathed in the faint glow of distant stars and the relentless sleet of galactic cosmic rays, which have slowly altered the chemistry of its surface layers. It may have passed through dense interstellar clouds, occasionally accreting a thin rind of new, foreign material. It has likely felt the subtle gravitational tugs of countless passing stars and rogue planets, each one minutely perturbing its path through the galaxy. The fact that we detected it at all is a statistical miracle. For every one of these objects we see, there are billions more cruising unseen through the dark spaces between stars. Its encounter with our Sun was a brief, fiery moment in an epic voyage that spans eons. The CMEs that struck it were perhaps the most violent event it has experienced in millions of years. And now, having passed through our system, its path bent but its course unshaken. It continues on its way. It will not approach another star for millions of years, perhaps longer. It is a perpetual traveler, a silent testament to the dynamism of the galaxy and the vast interconnected flow of matter on a galactic scale. We were privileged to witness a single frame in its unimaginably long movie. The complete story of 3I Atlas is not written in a single observation, but is woven from a tapestry of disparate data threads. To build a coherent narrative, we must combine the orbital data from the minor planet center, the high-resolution imagery from Hubble, the spectroscopy from JWST, and ground-based telescopes like the Gran Telescopio Canarias, the polarization measurements, the coronagraphic tracks, and the solar activity logs. Each of these datasets has its own strengths, weaknesses, and uncertainties. The Hubble data gives us size but not mass. The spectroscopy gives us composition but not internal structure. The coronagraph data gives us position but with poor precision. The solar data tells us about eruptions but not their precise targeting. The art of modern astrophysics lies in synthesizing these imperfect, sometimes contradictory lines of evidence into a single, most likely story. This is where Bayesian analysis and complex statistical modeling come into play. Researchers will create a multi-parameter model of 3I Atlas, its mass, density, composition, outgassing properties, and nuclear structure, and test thousands of variations of this model against the complete tapestry of data. They will ask, which model parameters best reproduce the observed photometry, the astrometry, the spectrum, and the apparent lack of deflection? This process will generate not a single truth, but a probability distribution. It will tell us, for instance, that the density is likely above 2 GC-3, or that the CO2 production rate is probably within a certain range. This probabilistic, evidence-based narrative is the most honest and powerful conclusion we can reach. It acknowledges uncertainty while progressively narrowing the possibilities. The final published paper on 3I Atlas will not be a dramatic revelation of what it is, but a careful, quantified argument for what it is most likely to be, given all available evidence. This is the slow, unglamorous, but ultimately triumphant work of science. As 3I Atlas continues its outbound journey, its coma will shrink, its tail will dissipate, and its reflected light will dwindle to invisibility. For a time, the largest telescopes may still track it as a stellar point, allowing for final, precise astrometric measurements. But eventually, even that will become impossible. It will cross an invisible threshold and pass from the realm of the observable back into the realm of the theoretical. It will become a data point in a catalogue, a line on a graph of hyperbolic objects, a subject for future PhD theses. Yet its legacy will be enduring. It has already left an indelible mark. It has provided a new, high-priority use case for chronographs, demonstrating their value in tracking objects through superior conjunction. It has spurred new theoretical work on plasma interactions at the Comet-Sun interface. It has given the teams planning for the Vera Rubin Observatory a concrete example of the kind of exotic science their instrument will enable. And for those who followed the story, it has expanded their mental map of the universe. The greatest legacy of 3I Atlas may be the questions it leaves behind. Questions that will hang in the air, unanswered, until the next visitor arrives. Was it truly an electromagnetic anomaly, or just a fortunate, dense rock? Does its CO2 richness represent a common class of interstellar object? The next one, and the one after that, will provide the answers. 3I Atlas is the herald. It showed us that the interstellar frontier is not barren, but rich with mystery. It reminded us that our models are incomplete, and that nature always has surprises in reserve. As it fades into the black, it carries with it our curiosity, our theories, and our hopes for a galaxy far stranger and more wonderful than we ever imagined. Our watch may be over, but the hunt has just begun. The profound mystery of 3I Atlas has sent ripples back through time, compelling astronomers to re-examine the data from our first two interstellar visitors with fresh, questioning eyes. The initial analysis of Oumuamua's non-gravitational acceleration focused on outgassing of hydrogen or nitrogen ice as the most plausible explanation, despite the lack of a visible coma. But in the wake of 3I Atlas's potential electromagnetic interactions, a provocative question emerges. Could Oumuamua's behavior also have had a non-mechanical, non-outgassing component? What if its strange acceleration was not solely due to jets of gas, but also involved a subtle, complex interaction with the solar wind and the sun's magnetic field? Oumuamua was tumbling, and its surface was speculated to be unusually reflective, possibly metallic. A tumbling, conductive object, moving at high speed through a magnetized plasma, can indeed induce complex electromagnetic forces. While the acceleration was small, the new paradigm suggested by 3I Atlas invites us to reconsider whether our models of these interactions are complete. Similarly, 2I Borisov, the normal comet, is now being scrutinized for any subtle anomalies it might have displayed. Were there any peculiarities in the structure of its plasma tail? Any unexpected brightenings or kinks that could be reinterpreted as signs of an enhanced interaction with a passing solar wind structure? This retrospective analysis is not about rewriting history, but about using a new key to try and unlock old doors. The hypothesis is that electromagnetic phenomena might exist on a spectrum. Borisov, with its thick, water-dominated coma, might have interactions dominated by collisional physics. Oumuamua, a bare, possibly metallic rock, might exhibit one type of effect. And 3I Atlas, with its CO2-rich, potentially highly conductive coma, might represent a third, more potent point on that spectrum. This creates a new theoretical framework against which all future interstellar objects will be measured, turning individual curiosities into a comparative science that seeks to understand the full range of behaviors exhibited by these galactic travelers. To understand where 3I Atlas came from, we must delve into the violent astrophysical processes that launch such objects into the void between stars. The prevailing theory is that these objects are ejected during the chaotic early stages of planetary system formation. As protoplanets coalesce from the dusty disk surrounding a young star, their gravitational interactions can fling smaller bodies, asteroids, cometesimals, and planetary building blocks out into deep space at tremendous speeds. The most efficient ejectors are giant planets. A close gravitational encounter with a Jupiter-sized world can provide a slingshot effect, accelerating a small object to beyond the escape velocity of its host star. This suggests that planetary systems with giant planets in wide orbits are likely prolific factories for interstellar objects. Another, more cataclysmic ejection mechanism is the death of a star. When a star like our Sun dies, it expels its outer layers as a planetary nebula, potentially disrupting the orbits of any surviving planets or cometary bodies and sending them adrift. In a binary star system, the complex gravitational environment can also easily eject material. The high velocity of 3I Atlas, some 60 km/h, provides a clue to its origin. This is significantly faster than the local standard of rest around our Sun. This velocity kick suggests it didn't just gently drift away from its parent star, it was violently expelled, likely by a massive gravitational perturber. Its trajectory from the galactic thick disk points to an origin in an ancient system, one that formed long before our own Sun, in a region of the galaxy with different chemical enrichment. It is a piece of galactic archaeology, and its speed and path are a permanent record of the gravitational forces that shaped its existence billions of years ago. It is a product of the galaxy's dynamic and often violent machinery, a single piece of debris from a construction project that was completed eons ago in a far-off corner of the Milky Way. For every 3I Atlas we detect, for every Oumuamua and Borisov that passes close enough and is bright enough for our telescopes to catch, there exists a silent, dark, and unimaginably vast majority of interstellar objects that we never see. Current estimates, based on our limited detection statistics, suggest that within the orbit of Neptune alone, there could be thousands of interstellar objects similar in size to 3I Atlas at any given time. And when we consider smaller objects down to the size of a house or a car, the number likely swells into the millions or even billions. Most of these are too faint, too small, or too far from the Sun to ever be detected with our current technology. They are the dark matter of the small body population, an unseen flux of material constantly passing through our solar system. This has profound implications. First, it means the resource base of our solar system is not fixed. There is a continuous, if subtle, rain of extraterrestrial material from other star systems, contributing a tiny but constant trickle of new elements and isotopes. Second, it dramatically increases the chances of panspermia. If interstellar space is this thick with material, then the probability of a life-bearing rock from one system impacting a habitable world in another, while still infinitesimally small, is not zero. Third, it represents both a future opportunity and a potential hazard. As we become a spacefaring species and establish infrastructure throughout the solar system, This population of unseen, high-velocity projectiles represents a navigational hazard that we will eventually need to map and monitor. Conversely, they also represent unparalleled scientific targets. Future advanced telescopes, perhaps stationed in the outer solar system, or equipped with powerful new sensors, may be able to detect and track these dark wanderers, opening up a whole new frontier for exploration without ever leaving our own cosmic backyard. 3I Atlas is not a rare exception. It is merely a visible representative of an immense, hidden population that permeates the galaxy. A subtle but profound philosophical issue raised by the study of 3I Atlas is the observer's paradox, a concept well known in physics. The act of observation can sometimes alter the thing being observed. In the case of a comet, our primary tool for observation is light, photons from the sun that strike the object and are reflected or absorbed, or that excite molecules whose emissions we then detect with our spectrometers. But this light is not a passive probe. The very sunlight we use to see 3I Atlas is the energy source that powers the phenomenon we are trying to study. It's outgassing. We are heating the object with the same light we are using to observe it. This creates a fundamental feedback loop. As we watch the coma develop and change, we are witnessing a process that is, in part, driven by the energy we are using to observe it. This is particularly relevant for the short-circuit hypothesis. If the object's interaction with the solar environment is as sensitive as proposed, could the act of observing it, of focusing immense radio telescopes on it, for instance, or of using active radar, introduce a confounding variable? Could we be inadvertently stimulating a response that we then misinterpret as intrinsic behavior? This is an extreme and unlikely scenario, but it highlights the complex relationship between the observer and the observed in astronomy. Our models attempt to separate these effects, to subtract the known influence of solar heating from the object's intrinsic properties. But with an object as alien as 3I Atlas, can we be certain we know all the pathways through which energy is absorbed, stored, and re-emitted? The object we see is not a pristine interstellar traveler. It is that traveler being processed and altered by its passage through our system and by our own act of looking at it. This does not invalidate our data, but it adds a layer of complexity, reminding us that what we see is always an interaction, a relationship, not an absolute truth. As of this moment, the story of 3I Atlas remains unfinished. It is a narrative suspended between data and interpretation, between established fact and tantalizing speculation. The final synthesis, the chapter that neatly ties all the loose ends together, has not yet been written. It may not be written for years. The object itself is now beyond our grasp, its truth receding into the interstellar night. The final resolution will come not from a single eureka moment, but from the slow, cumulative weight of evidence. It will come from the publication of that crucial, peer-reviewed paper that presents a definitive analysis of the coronagraph astrometry, putting error bars on the non-deflection. It will come from a thorough review of solar data that either confirms or refutes the timing and targeting of the far-side CMEs. It will come from laboratory experiments that simulate the behavior of CO2-rich ices under solar wind bombardment, and from advanced magneto-hydrodynamic simulations that model the plasma interactions with ever greater fidelity. And most importantly, it will come from the next visitor. Interstellar Object 4I, when it is discovered, will be the ultimate test. If it, too, shows a mysterious resilience or an anomalous electromagnetic signature, then the case for a new phenomenon becomes compelling. If it behaves exactly as predicted by Newton and Kepler, then 3I Atlas will be relegated to the status of a fascinating outlier, a case of fortunate coincidences and measurement uncertainties. But even that outcome is a form of progress. Science advances as much by clarifying what is not true as by discovering what is. The journey of 3I Atlas, from its discovery as a faint smudge in a telescope's eyepiece to a subject of global fascination and intense scientific debate, is a testament to human curiosity. It is a story that encapsulates the very spirit of exploration, the drive to understand the unknown, the courage to question established doctrines, and the humility to accept that the universe is always more complex, more subtle, and more wondrous than we can possibly imagine. The final page on 3I Atlas may be blank, but the volume of which it is a part, the story of our quest to understand our place in the cosmos, remains wide open, waiting for the next mysterious traveler to arrive and prompt us to write a new and perhaps even more shocking chapter. Thanks for watching.